Hello everyone. So in this video we are going to discuss the second half of third unit. So in this particularly we are going to discuss what are the types of optical receiver circuit. So as we already discussed in our last video, we know that what is the actual syllabus of third unit. So the first half of third unit which deals with the sources. And the second half of third unit is nothing but optical detectors. So in that last video, we have discussed what are the types of photodetector, what is the purpose and what are the characteristics. Now in this video, we are going to discuss about noises, that is noise sources, and we are going to evaluate the signal to noise ratio. So first of all, we signal to noise ratio. So if you just consider this photodetector noise, we can say that any optical detector or photo detector, so that can be evaluated, that is a performance of any optical receiver that can be evaluated by using the parameter called signal to noise ratio. So this photo detector noise is from the statistical nature of photons to electron conversion process. So that is the optical signal is converted into electrical signal. So we can say that the conversion process is photon to electron conversion process. Now this performance of this optical receiver that can be evaluated by using this parameter called signal to noise ratio at the output of optical receiver. So that is the purpose why we consider the signal to noise ratio. And in general, what is signal to noise ratio is, that is according to the photodetector. And here it is signal power from the photocurrent to the photodetector noise power plus amplifier noise power, which means as we know that optical detector or optical receiver is nothing but mainly which is consist of optical detector as in first block, and second block is nothing but pre-amplifier. So definitely there will be a noise due to the photodetector, and there will be a noise which is associated with the amplifier. So basically we'll be just classifying the types of noises into two parts. One is the noises which are associated with the photodetector, and second one is noises which are associated with the amplifier circuit. So that will be substituted in the denominator. So obviously numerator is nothing but which is the signal power from the photocurrent. So that is the actual output current from the any detector circuit. Now this noise sources in this receiver that arises from the photodetector noise and the thermal noise. So this amplifier noise, which is also called as thermal noise. In other words, we can call it as Johnson noise also. Okay. So basically, and then what is the requirement for the signal to noise ratio? So what should be this value? So generally speaking, for any optical receiver or any receiver circuit, which will be consisting of an amplifier there. So the signal to noise ratio, to achieve this high signal to noise, actually this signal to noise ratio should be very high, which means this numerator value should be high. At the same time, this denominator should be as low as possible. Why? Because the denominator is nothing but which is the noise power from the photodetector and noise power from the amplifier circuit. So it should be as low as possible, which means there should not be any noise power. Okay. So to achieve this high signal to noise ratio, what are the requirements? That is the first one. So to achieve this high SNR, first of all, this photodetector, you should have the high quantum efficiency. We know what is quantum efficiency is. Okay. So you should have the high quantum efficiency to generate the large signal power. So that will be substituted in the numerator. And next is nothing but, so this photodetector and this amplifier noises should be kept as low as possible as I told you. So this is the requirement to achieve the high SNR value. So higher the value of SNR, better the performance of any receiver circuit or any amplifier circuit. So this is the purpose why we go for the signal to noise ratio evaluation. So first of all, we have to just consider what are the types of noises. So as I told you, this optical receiver noises that can be broadly classified into two types. One is photodetector noise, other one is amplifier noise. Why? Because this optical receiver, which consists of mainly two important blocks. One is photodetector noise, second one is amplifier noise. Now this photodetector noise, again it is classified into two types. One is quantum or short noise, second one is dark current noise. This dark current noise, again it is classified into two types. One is bulk dark current noise, next one is surface dark current noise. The surface dark current noise, which is also called as surface leakage current noise. And next classification is that the noise is associated with the amplifier. So this amplifier noise, we can call it as either thermal or Johnson noise. So this is about the types of noise sources associated with the optical receiver overall. Okay, one by one. So this is the equivalent circuit of optical receiver. So this is about the photo detector with, that is the overall optical receiver, which means which consists of optical detector, which is nothing but photodiode, which is connected with the preamplifier circuit. And this is the equivalent circuit of this photo detector receiver. So we are going to find out the what are the noise powers in terms of mean square value of current. So before going into that mean square value of current due to that particular noise, which is very important that we have to find out the primary parameter called photocurrent. So what is the photocurrent which is generated from the photodiode? So which can be represented as photocurrent at time t, we can write it as eta q by hv into optical power at that time. So eta is nothing but quantum efficiency, q is nothing but charge of electron, h is nothing but, that is hv is nothing but photon of energy. So v again it can be replaced as c by lambda. Finally we can just substitute that v is equal to c by lambda. So this is about the primary current, which consists of, that is DC value, and which is also, it is nothing but average photocurrent, that is due to the signal power. Now we can just able to find out what is the mean square signal current. So mean square signal current we can just find out value as I square is equal to, it is IP square of t, where S is nothing but variance. Sigma S square into P is nothing but, here it is variance value. And similarly for the avalanche pin photodiode, we can just represent it as PIN. And if it is an avalanche photodetector, then we can just represent it as APD. Now, where this capital M is nothing but only for the avalanche photodiode, there is a factor called M. Why? Because this there is a pin photodiode is nothing but non-multiplying type. So, we will be just representing only in terms of current. But here this avalanche photodiode is nothing but it's in multiplying type. So, there will be an avalanche multiplication factor capital M. So, that will be represented in terms of M square here. So finally we can able to write that what is that photocurrent, that is mean square value of photocurrent, that is equal to m square by 2 into IP square, where IP square is nothing but it's an photocurrent. Now this is the primary parameter that can be used to find out the remaining signal powers due to the types of noises. So first comes quantum or short noise. So when there will be in quantum or short noise, as we know that quantum or short noise, which is mainly due to the photodetector circuit. So this quantum or short noise, which is mainly arises from the statistical nature of production and collection of the photoelectrons when an optical signal is incident on a photodetector. The short noise current as a mean square value in the receiver bandwidth BE, that is proportional to the average value of the photocurrent. So that can be represented as I square short, which means short noise, mean square value of short noise current, that is equal to 2QIP into bandwidth. And this M square is nothing but avalanche multiplication factor, and F of M is nothing but figure of merit. If it is in pin photodiode, both this M value and figure of merit is equal to unity, so that we can write it as 2QIP into BE. BE is nothing but bandwidth. That is receiver bandwidth, so it will be represented as BE. So for that, to find out that mean square value of that is current, mean square value of current due to that short noise, we can use that formula 2QIP, where IP is nothing but photocurrent into bandwidth. And next comes dark current noise. So what is dark current? First of all, when there is no light signal is incident on the highly doped region, what will happen? And still there will be minority carriers, moving of minority carriers. So due to that, there will be a very smaller value of current that will be flowing in the reverse bias condition. So that is called as dark current. So which means that when no light is incident, there will be a small amount of current that will be flowing in the circuit. So that is called as dark current. So due to this dark current, again there will be chances of noise. So that noise we are just calling it as an dark current noise. So this dark current noises, it's in sum of both bulk and surface current. So bulk dark current which which is mainly due to the electrons or holes that are thermally generated in the PN junction of the photodiode. So therefore we can able to find out the mean square value of dark current as I dB square, which means dB is nothing but dark bulk current which is equal to 2qid into bandwidth. Actually, this m square f of m is that is equal to 1 for the pin photodiode. Only for the avalanche photodiode we have to write this. So 2q id into bandwidth. So here we'll be substituting that photocurrent. Why? Because here this photo generated carriers, but here it is dark current. So that we'll be substituting that id alone. So next one is nothing but surface dark current. So we can able to find out the mean square value of the surface dark current. First of all, what is the surface dark current, which is also called as I told you, it is also called as surface leakage current, or simply we can call it as leakage current. So which is mainly depends upon the surface defects. Sometimes there may be in cleanliness, or sometimes it may be due to the bias voltage fluctuations, or due to the surface area of that material, there may be in noises. So due to that noise, there will be a flow of current. That current is called as surface dark current. Okay, so that will be calculated by using that formula 2qil into bandwidth. So first of all, this quantum or short noise that can be calculated just by substituting that photocurrent IP. In similar way, the dark current noise that will be calculated by using, that is by substituting that dark current ID. And now the surface dark current that can be find out, that can be calculated by using that load current IL. So this load current, actually this IL is nothing but surface leakage current. So leakage current we just will be different, that is expressing in terms of L. So IL is nothing but leakage current. So by using this formula we can able to find out the surface leakage. And next one is, now we can just add that all the mean square values of photodetector noises together. So first comes mean square current value due to the short noise. Next one is mean square current value due to the dark bulk current. Next one is due to the, that's the surface leakage current. So all together we can just add it in this equation. Now next noise comes thermal noise. So as I told you, this thermal noise, which is also called as Johnson noise, which is mainly due to the amplifier circuit present in the receiver. So to simplify the analysis of this receiver circuit, we should assume that and there is an amplifier input impedance which is much greater than that of load resistance. So definitely there will be a thermal noise which is much smaller than that of RL. Now this photodetector load resistor contributes the mean square thermal noise. We can also call it as Johnson noise. So that can be represented as I square T, which is equal to 4 kBT by RL. So as we know, since it is also called as thermal noise, so thermal is nothing but it's in temperature dependent. So definitely in this equation it is temperature dependent, so that is capital T. So capital T is nothing but temperature, and KB is nothing but Boltzmann constant. Now by substituting all these values, and B is nothing but bandwidth and RL is nothing but load resistance. Now by substituting all these parameters in this equation, we can able to find out the mean square value due to the thermal noise. Substitute in the signal to noise ratio as we discussed in the first slide. So it is the ratio of this photocurrent, that is the signal power from the photocurrent, and which is multiplied with the m square if it is an avalanche photodiode. Suppose if it is an pin photodiode, this m is equal to 1. And in the denominator we'll be substituting all the mean square value due to the different types of noises. Finally we can able to find out the signal to noise ratio. Now the signal to noise ratio, when this optical power is relatively high, then the short noise power is much greater than that of thermal noise. So in that case we can say that signal to noise ratio, it is also called as short noise limited or quantum limited. Suppose when the optical signal power is low when compared to the thermal noise, then we can just call that signal to noise ratio as thermal noise limited. So either we can just call it as quantum noise limited or thermal noise limited, based upon the which of the noise signal is greater or smaller than that of the particular noise signal. So this is about the signal to noise ratio. So as we discuss, higher the value of signal to noise ratio, better the performance of the optical receiver. So that is the purpose we'll be evaluating this signal to noise ratio for the optical receiver circuit. And this is the formula to find out that what is it multiplication factor in case of avalanche photodiode. And by using this m value and this x is not here, this x is, this is the optimum gain at the maximum signal to noise ratio. So that will be represented in terms of this equation. And by setting this resultant value to 0, we can just solve the value of m. So when m is equal to 1, we can say we can call it as it's a pin photodiode. And if it is a value for that m, then it is called as avalanche photodiode. So like this, we can able to find out the factor also. So next comes the one more important parameter called noise equivalent power. That is the sensitivity of any photo detector in an optical fiber communication is in terms of minimum detectable optical power. That is, this is the optical power which is necessary to produce a photocurrent of the same magnitude as the root mean square value of the total noise current, or equivalently signal to noise ratio of the that is the signal to noise ratio of unity value. That is, this is the optical signal power which is refers to as noise equivalent power, or we can call it as NEP, and which is represented in terms of watts per root of hertz. Now, for example, this is the thermal noise limited case for a pin photodiode. We can be able to find out this noise equivalent power by using this formula, root of 4 kb T by RL by R, where R is nothing but responsivity, RL is nothing but load resistance, T is nothing but temperature. So, okay, so I'll repeat it once again. So, the main purpose of this noise equivalent power is to find out the sensitivity of the photodetector. Okay, and in terms of this noise equivalent power, we can say this is the minimum detectable optical power from the any photodetector, and that is called as noise equivalent power. So that can be calculated by using this formula. So this is also one of the parameter for the photodetector is concerned. Listening. Thank you.